Welcome back. We're making a shift now. We're still talking about dynamics in biology, and well, as I've already said, that makes sense. Biology is about dynamics. It's ever changing, but we're changing our perspective here because now we're going from thinking about rate equations for the mean values to the chemical master equation. And the virtue of that is that we're now going to reason about the time evolution of the entire probability distribution. That's what this will bring to the table. And my first example, we've already done an example of the chemical master equation for diffusion, and that was cool. It was one of our three methods. It was the last one. And now we're going to bring those same ideas to bear on a completely different problem, and that's going to be part of the fun of this, is that we're going to look at a bunch of different problems from the same perspective. So my starting point is a reminder that we already talked about in the context of the Poisson distribution when we were doing the great probability distributions. And that has to do with asking the question, what is the distribution of mRNA counts? Said differently, I have a bunch of cells. In each cell, I ask it how many mRNAs of the particular mRNA of interest do you harbor, and I do that again and again and again, and then I make a histogram, and that histogram reflects the counts of the different numbers of mRNA per cell. In this case, what's shown on the right is actually over all genes. So this is not a single gene copy number, but this is instead just to give you a sense of how one would do a fish experiment. It's just a reminder on that point. So in some sense, the histogram is irrelevant to what I want to say. So forget about that. The thing that's relevant is just to note that if I wanted to count a particular mRNA, one of the ways of doing that, as shown here, is that you tile that mRNA with a series of probes, let's say on the order of 50 distinct probes, each of which binds a different region of the mRNA. And then what you do is you count, so that leads to puncta, and then you count those up, and that gives you your single molecule distribution. Here I'm just showing you exactly how such a thing would go. So in the left column, I have all of my different cells. The first one has 2 mRNAs, the second one has 1 mRNA, the third one has none, the fourth one has 3, the fifth one has 1, and so on. And then what I do is I group them. So what I mean by group is I say how many of them had 0, how many of them had 1, how many of them had 2, how many of them had 3, and from that I can compute the probability distribution, which is what I'm showing you on the right. The probability distribution is the probability of finding a cell that has 0 mRNAs, finding a cell that has 1 mRNA, finding a cell that has 2 mRNAs, and so on and so forth. So that's the concept, which is there's an experimental measurable. This is better, if you like, than the mean, which one gets from the population. This is more targeted. It's more intense. It puts higher demands on us as theorists, in the sense that the slogan of the course, quantitative data demands quantitative models. Well, when you can't measure the distributions, there's less pressure on us theoretically to calculate them. But once we can measure these things, then the pressure is on us to no longer accept words as the language of this subject. The language is mathematical. We need to respond in kind to the experiments. So that's what that's all about. So now what I want to do is I just want to give you an indication of the things that can happen in an instant delta t. In other words, at time t, the disposition of the cells is shown here. So these are the cells that I'm looking at. And then in a time step delta t, the first cell actually synthesized a single mRNA. So there was a transcription event. For cell number 2, there was a degradation event. So after a time delta t, prior to the time delta t, at time t, there was a single mRNA. The degradation process occurs. Now I have a cell that has no mRNAs. The third cell, there was production. The fourth cell, there was no event at all, and so on and so forth. What that does, though, is it leads to a time evolution for the entire distribution. This is the initial state that you see down here, and then this is the final state, gotten by basically histogramming and normalizing the various counts. And so our interest is, how do we go about making a theory that allows us to find the time evolution of the mRNA distribution? The answer to that, for this purpose, is the chemical master equation. So that's the tool that we're going to unleash on this problem and on many others. So the point of this figure is just to show you, once again, like I did in the context of the MWC model, this idea of sameness. So it depends on how you're talking about a system. Yeah, it doesn't involve the same molecular players, so it's not the same in that sense. But at a higher level, when you view it mathematically, it's the same. In other words, exactly the same mathematics describes, for example, the conformations of a polymer, as shown here, and the diffusion that you see up here. It's literally the same thing. And so what we're going to do is we're going to work out the chemical master equation for the mRNA distribution for a constitutive promoter, which is the thing that's shown here. We've already talked about the constitutive promoter. And what we want to do is we want to work out the temporal dynamics. The goal is to find P of M and T, where P of M and T is the probability of finding mRNAs when I grab a cell at time t. So that's what I'm trying to do. Sorry, my writing is terrible. It's a little awkward the way I'm sitting. So that's the plan. I don't think that is any big deal. So I think what I want to do is I now want to try to actually to write this out. So our goal is to write the probability of finding mRNAs at time t plus delta t. And as we have done already a number of times before, we're going to say that that's equal to probability of finding mRNAs at time t. And then what we're going to do is we're going to find all the ways to add to the little skyscraper at position M on the histogram, and all the ways of subtracting from that histogram. So one of the things that could happen is that I could transcribe if I'm currently an M-1, right? So in other words, the transition from I'm going to give it a green arrow, from this skyscraper to that skyscraper, it gets a green arrow because it increases the height of this particular skyscraper. So that was what that term is. So this guy I'm going to draw like this. Next, I'm going to do another plus sign term, which is plus gamma delta t times m plus 1, and then the probability of being an m plus 1 at time t. Now what's this all about? I'm going to give this a green arrow because it increases the skyscraper at m, and that corresponds to this to this arrow. So if I'm currently an m plus 1 and I degrade in the next instant, I become an m. That means I went from being an m plus 1 to being an m, and that means I increased the quantity of m. So that's what that one is about. And then I have a minus r, I have a minus r delta t times being a p of m at t, because this is basically this arrow, which I will draw down here. So I'm in the mth skyscraper and I go to the m plus 1th because of synthesis. And then the last one, you can already guess, is going to be this one, which is minus gamma delta t, and then m times p of m and t. And that's this arrow. So those are the 4 ways in which I can change the height of the skyscraper at position M. That's it. So in a sense, this is all we need. And let me say, for the homework, you'll have an opportunity to try this out, where you will implement it in Python, and the sort of thing that you'll pursue is shown here. So notice at t equals 0, so the time axis is in this direction, and at t equals 0, this is a spike at mRNA count 0. So the way I want you to think of this is that these are uninduced cells. At t equals 0, I take my pipette, I pipette in some inducer, and then what's going to happen is that over time, the cells will start to produce mRNA, and in the long time limit, I will adopt the steady state distribution, which you see over here. But this is the time axis. So this is time going in this direction. And so in the early times, we're mainly concentrated at low mRNA counts, and then over time, we hit this average, which you'll remember is R over gamma. So that's the average height of, the average number of mRNAs that you will have in the long time limit. So in a way, this is all the math we need, but let me make a few observations. So observation number 1, this is kind of that Michelangelo moment. This thing wants to be a differential equation. So if I subtract P of M and T from both sides and divide by delta T, what I will get is dPm by dt is equal to R P of M minus 1 comma T plus gamma M plus 1 P of M plus 1 and T minus R P of M and T, and then minus gamma. I guess I need to keep these parentheses. Gamma times M times P of M and T. Just an aside, what's up with this thing and this thing? So gamma delta T, so maybe I should make a note. Gamma delta T is the probability that a given mRNA will decay in a time step delta T. But the thing is, I don't have one mRNA that could decay. I have M of them, or M plus 1. Up here I have M plus 1 of them. So every one of them has the likelihood gamma delta T of degrading in the time step delta T. So I have to multiply by how many of them there are, because each of them is a candidate for destruction in that time interval. So anyway, this is the differential equation form of the master equation for the constitutive promoter. And the other thing I want to say is observation number 2 is that in steady state, P of M is equal to R over gamma to the M power, e to the minus R over gamma over M factorial. This is the Poisson distribution. And I'm not going to repeat the derivation because I already did this when we talked about the Poisson distribution in the context of probability distributions. So I invite you to go back over there to see. I didn't really say it was the master equation at the time. All that we did at that point, you might remember, is we set up what I'll call detailed balance in the sense that we looked at a given interface and we just made sure that the amount flowing right and the amount flowing left balanced each other on every one of these interfaces. So that was the logic of what we did, and when we did that, it led us to this distribution, which is the Poisson distribution. Note that lambda equals R over gamma is the average number of mRNAs. And this is a one-parameter family of possible distributions. In other words, once you tell me the average, I've already said this before, but I'm reiterating it. Once you've told me the average, I have no other fitting parameters. So the distribution is the distribution. So that's what I wanted to say for our first introduction to using the chemical master equation in a setting other than diffusion. And you see that spiritually that the concept is very much the same. We have these skyscrapers, and all we're trying to do is find the rules of how the heights of these skyscrapers change in each time instant delta t, The reasoning is that there's microscopic processes that transpire. In the case of diffusion, it's hops. In the case of transcription, it's transcription and degradation of mRNAs that are responsible for these dynamics.